In this next tutorial, we will use the definition of continuity to determine if a function is continuous or not. So let's get to this page of our notes, continuity. Now, the simple way to explain when a function is continuous is you can draw it without picking up your pencil. That's a pretty simple way of doing it. Mathematically speaking, the definition for continuity, a function f of x is continuous at every domain point. In this case, I'll talk about the domain point C, if and only if these three things are satisfied, all three of them. So let's look at the first one. F of C is defined. What that means is I have to put the domain point into my function and there has to be an output clearly defined. Okay, step 2 or part 2, the limit as x approaches C of our function has to exist. So that means that the left side of C and the right side of C both have to be approaching the same value, so therefore the limit will exist. And part 3, the limit as this is what links these two things together. The limit that we just found in part 2 has to be equal to the output that we find in part 1. So all three of these have to be true for our function to be continuous. Let me show you an example of a function that is not continuous so we can see what rule it's breaking, I guess. So let's say we've got this function right here and it does this. Now clearly this is not a continuous function because I had to pick up my pen to draw it. But let's see what rule it's breaking. Rule number 1, f of c has to be defined, and I'm just going to make my domain point the 3 right here. F of 3 has to be defined, which it is. Here's a point right up here, so f of 3 is defined. We have an output. Step 2, part 2, the limit as x approaches R3 of this function must exist, which it does. If we approach 3 from the left side, the value of the function is approaching this hole, and from the right side, the value of this function is approaching this hole. So that limit exists, and it's right here. So what it must be failing is this one, where the limit and the output are not the same, and that's clear. Our output is up here, but our limit is down here, and that's why this is not continuous. So that's an example of something that follows two of the three things, but not the third one. Let's look at example 3 and see if we are continuous. And I think we're going to be interested to see if we're continuous at the point 1. So let's see what we've got here. I'm actually going to draw a picture of this because I like the graph, and we can see what the graph looks like. I'm going to go up to 4 since I know I'm going to need to do that, and I'll go over to 3, I guess, right here. Let's graph the first one in one color. I'll do red. This is just the graph of a line. It crosses the y-axis at 4 and has a slope of -1. So I'm going to cross right here and have a slope of -1. I'm actually going to put an open circle here because I know that we don't actually have the value of 1. So that's what this piece of the graph is going to look like. It's a piecewise. And I'll graph the other one I'm going to do in blue. This is a quadratic. I might just plug in using a t-table. Obviously, I can't plug in a 1, so I'm going to plug in a 2. 4 times 2 is 8, minus 2 squared is 4. So when I plug in a 2, I get 4 as an output. And let's plug in a 3 real fast. That's 4 times 3 is 12, minus 3 squared, which is 9. 12 minus 9 is 3. So if I plug in a 3, I output a 3. And I can see that if I had plugged in a 1, I would have outputted a 3 as well. So I can see that this is that part of the curve. I just did a quick little t-table to see that. So that's a picture of my piecewise function. So perhaps we check our one-sided limits. The limit as x approaches 1 from the left side, and I'll just call it of f of x. So the left side of 1 would be numbers that are less than 1, so I would be using this top piece. So I'd be plugging a 1 directly into this, and 4 minus 1, I'll do 4 minus 1, and that's equal to 3. So the left-sided limit exists. It's 3. Okay, that's cool. Let's plug in and find the right-sided limit. that means 1 with a little plus sign, and I'll just call it of f of x. For the right-sided limit, we want to be on the right side of 1, which are numbers that are greater than 1, so I'd be using this piece. And if I plug a 1 directly into here, I get 4 times 1 minus 1 squared, which is also equal to 3. So if I'm talking overall, my limit, the left-sided limit is 3, the right-sided limit is 3. That must mean that the limit overall, as x approaches 1 of f of x, is equal to 3. So that's cool. That means that part 2, that the limit exists. So the question is this function continuous? Well, we already know the answer to that because we're already looking at the picture and it's missing something. It's not defined at all when x equals to 1. This is not continuous. It's continuous every other place in our function, but it's not continuous at x equals to 1. Unfortunately, even though the one-sided limits existed and they were the same thing, so therefore the overall limit existed, we are not defined when x equals to 1. So there's one thing we could do to f of x to make this actually a continuous function. And it's as simple as this. All we needed to do was include the domain point of 1. If this were a less than or equal to, then this would be a continuous thing because we'd fill in this open circle. Or if we erase that and we said that this is greater than or equal to, then again, we'd fill this open circle in and it'd be a closed circle and it'd be continuous. So if we would just change one little thing, just fill in the hole, then we would be continuous. But until then, we are not continuous because it's breaking rule number 1 and therefore it's breaking rule number 3, excuse me. Let's look at example 4. I can see now that the domain points include all values because I see that it's including the 2. I wonder if that means that this instantly is going to be continuous. Well, why don't we look at the limits? Let's look at the one-sided limits. We're talking about 2, of course. So let's say the left-sided limit. If I'm looking for the left-sided limit of 2, I'm going to be using this part of the domain, so therefore this piece of the function. Plug a 2 into there and I get 4. The right-sided limit, that's 2 with the little plus. Let's see, this time I'd be using numbers that are greater than 2, and I'd be using this piece. Plug a 2 directly into there and I get 6. So what does this mean? This means that the overall limit does not exist, and therefore this is not continuous. So my point is, even though you are including all domain values, that does not mean anything. We still are not continuous in this case when x is equal to 2. I guess to finish our notes, I feel like we're maybe just a little bit incomplete. The limit, the overall limit, does not exist. And again, the reason that it does not exist is because the left-sided and right-sided limits do not equal the same number. And since the limit does not exist, that's breaking part number 2, and therefore we're not continuous. Thanks for watching this continuity tutorial, and I'll see you in the next one.